Hi, this is Dr. Johnson, and it is Lecture Module 3, RTL System Verilog for former ECE 270 students. So you should already be familiar with a variety of basic Verilog syntax, and we've been reviewing it in the laboratory content as well. And you would have already had a C programming class as well, and the syntax of Verilog derives quite a bit from C syntax. So we will be drawing upon that. Now, a lot of the syntax review is in the laboratory portion, so this module is by no means a comprehensive coverage of System Verilog. Rather, its purpose is to fill in gaps that are left between what we do in the labs, what you've had previously from ECE 270, introducing some new concepts that we'll be using in System Verilog, as well as going back over some of the more difficult concepts, both in Verilog and System Verilog. So in part 1 of this lecture module, which will be the entirety of this recording, I'm going to address a number of topics that students have historically found tricky and have tended to make mistakes in the use of these things. One of the concepts that students may find tricky is the distinction between blocking and non-blocking assignment. So here on the top, I have a question that I put forth that in the live lecture I would make as a clicker question. In this case, I will explain it, although I'll let you think about the question for a moment. But now I'm going to go ahead and answer it. So blocking assignment is the type of assignment that appears in a procedural block, and it has just a simple equal sign for the assignment. Now that's the syntax for it, but what it does is it assigns a value to a variable, and that value is available immediately for use by statements further down inside that always block. Now, if we were talking about C code or most programming languages, it would seem strange that we would even make a distinction on this point. But in hardware, when, let's say, A and B produce a value that then is output by a logic gate, there is a propagation delay associated with it. So that value isn't available immediately, and so at a given instant in time, the value of y at that instant would reflect the previous value of temp1 rather than the new value. But when we're simulating behavioral Verilog code, and we're only wanting to describe the logic function, not trying to model circuit behavior and delays and things, it is useful to have the value available immediately. Now, that's a blocking assignment. Non-blocking assignment is where the value is not available immediately. So if I take input I to this block and assign it to ST1, and then I have a statement ST1, the value of it gets assigned to ST2. Well, what I just described, the new value of ST1 caused by this assignment is not immediately available to this statement. So what will be assigned here is actually the previous value of ST1. And this, in fact, is more representative of the behavior of hardware. Now, in this context, it's inside of an always FF block, which is what we use for creating registers composed of flip-flops, thus the FF. And in this case, we are sensitive to the positive edge of the clock, which most of what we do will be that way. Some things we write will have a reset, but this does not. So at a positive edge of the clock, ST1 takes the value of I, and ST2 takes the previous value of ST1. So having said that, which of these pieces of code do you think create flip-flops? Well, hopefully I've said enough here that would give you some clues. One, the notes here right here say that this is combinational logic. Flip-flop is a kind of sequential logic. It's not combinational. So that alone would tell you. Conversely, over here, we have a clock edge sensitive function, and a value gets assigned to the output on a clock edge, which is a way of describing the behavior of a flip-flop. So we've got a variety of evidence that these are flip-flops. This is combinational, but there's a little more to this piece of code, and that is what this really represents is two flip-flops daisy chained. So this line represents one flip-flop where input I is the input to a flip-flop or a register that has ST1 as the output, and then the output of that register goes to another register at the input, and then the output ST2 is the output of that register. If we were to draw a schematic, and in this case these are 1-bit values, so really the schematic for this would look like a synchronizer. Couple important points to take away from this. One is that when you are writing sequential code, which is sensitive to a clock edge, you should use non-blocking assignment. When you are writing combinational logic, then you should use the blocking assignment. And we'll run into more examples that may make the need for this obvious. And it is possible to write sequential code with blocking assignments, but there are hazards associated with this. You can get in trouble in the source code simulation if you use blocking assignments. In fact, here I can describe it fairly simply. If these were blocking assignments such that I gets assigned to ST1 immediately, then that means at that same time instant, the new value of ST1 is available at ST2. So it's really eliminated the second flip-flop because this input appears at both outputs at the same time. Yet what we're trying to describe is two flip-flops chained together, and the only way to achieve that function reasonably is to use the non-blocking assignment. So we'll go forward. We'll run into more examples of the differences between these. Another feature of Verilog that may seem a bit mysterious when you first encounter it is the distinction between wires and reg types. And the reg type, even though it stands for register, it doesn't mean necessarily that a register in the circuitry will be created. Really, it would be much better if this had been called a variable, because the way reg types work in Verilog is much more like the way variables in a conventional programming language or a sequential programming language would function. The wire type is a bit more intuitive in that it fairly directly corresponds to the presence of a wire in the resulting circuit. That's not to say that the synthesis software might optimize it away if it figures out that it isn't needed when it combines some other logic somewhere. But aside from optimization considerations, a wire is going to imply the existence of a physical conductor. And so when you declare a wire, you will use it to connect different pieces of Verilog code to each other. There are some restrictions on how you can use wire types. One key restriction is that you can only assign values to it using assign statements, and assign statements can only be used outside of procedural blocks, so you shouldn't be using an assign statement inside an always block, for example. Now, some simulators, I think students may have discovered that QuestSim actually permitted this, but it's really permitting something that's outside the specification of Verilog. Now, even though you can only assign values using an assign statement to a wire, you can read the value from a wire inside a procedure. So a wire can be an input to any kind of code that's being used to describe hardware, but only an assign statement can set a value to it. Okay, that's the wire. This is another case of a clicker question. If we were in class, I would have asked you to determine which of these it is. Now, in the other column, we have a description of the way variables are treated, or reg types. So a variable should only be modified inside one module and inside one procedural block, which in a way is similar to the advice in other programming languages that you don't want it to act like a global variable being assigned from many different places. So the scope should be limited to the module or even the block of code inside the module where it is being used. If you assign it from multiple places, it's possible to do in simulation, but you're likely to get behavior that's hard to predict. But on top of that, you won't be able to synthesize hardware that replicates that behavior. In hardware, if you have multiple assignments to the same wire, and variables in Verilog sometimes do translate into wires in the circuit, but assigning multiple values in hardware, unless you're using a tri-state buffer so that only one gate at a time can assign or can force a value on the wire, you'll get conflicts and things like unknown values, at least in the logic simulator. So you really should only be assigning the value in one place. That's going to be true of wires as well. So that's not just a limitation of use of variables. Now, how a variable translates into hardware is less obvious than it is in the case of a wire. I said the wire fairly directly implies a physical wire in the circuit, whereas a variable can translate into a lot of different things in the final circuit, and it's not unusual for that variable to not correspond to directly anything in the final circuit. So some of the things that it may produce, if the variable is taking the output of one block of code and feeding the value to another block, then it's likely to end up being a wire. It's connecting two different pieces of code in that case. If you use the always FF syntax with clock edge sensitivity and you assign a value to a variable, then that variable ends up being the output of a flip-flop or a register. So that's the one case where the name reg maybe corresponds to the hardware it produces. But it is also possible that the variable may just be an intermediate value inside the code that helps you describe the logic, but when the synthesis software analyzes the code and figures out how to build the circuit, it may not correspond to a wire at all. Another way this can happen is, for example, you can have for loops in the procedural code, and the index variable for the for loop usually just disappears in the final circuit because each iteration of the for loop in Verilog ends up just corresponding to another copy of the circuitry required to implement the contents of the for loop. Again, this is something you'll see examples of. Okay, more restrictions on variables. The values can only be assigned within procedural blocks, and in your case, that's almost always going to be an always block. In fact, in hardware code, it will be some kind of always block where it gets assigned. Or in the test bench, you could be assigning values to a variable using an initial block. A point here is that, well, it's really just a reminder of the blocking versus non-blocking assignment. And both of them can be used with variables. Really what makes the difference is whether you are describing combinational logic where you would do blocking, or non-blocking would be sequential logic. Let's see. This I've really hinted at in my earlier discussion on this slide, which is that a procedural block will write a value to a variable. A procedural block could write values to multiple variables, but then that variable could appear as an input in another procedure. And so the output of the procedural block that assigns a value to this variable, that value is immediately available to some other block as an input. Let's see, one other point I want to make from this slide, backtracking to a wire. It says you cannot initialize a wire. Why not? Seems like a nonsensical statement. Well, it is nonsensical, but students will try to do this in their code, not realizing that they're doing it. So you will declare a wire or a variable, really, and assign an initial value. Maybe you declare the variable and you say the initial value is 0. Well, that makes sense in simulation, or when you're executing a program on a computer, you assign a value to a variable, you use it later. But in a circuit, if that variable or that wire type corresponds to a wire, all it can do is connect things to each other. Even if you assign an initial value during simulation, that initial value will be ignored basically during synthesis. All that matters in the circuit is what circuitry is putting a value on that wire. So the wire itself you can't initialize. Even if you try to, it won't. The only way you could initialize a value that ends up appearing as a wire in the final circuit is if it is an output of a flip-flop or a register. With a register, you can have a reset function on it that forces a value on it, and in circuitry you would typically have the reset asserted, say, on power on. So that you can initialize by applying a reset, but otherwise can't initialize it. Yet another point of confusion among students is the meaning of the values x and the values z on a variable or a wire when you're simulating a design. A value of x means unknown. And incidentally, I should say, in case constructs, x and z can have special meanings where they're used as wildcards. But when we assign a value to a variable or a wire, x and z have a specific, I guess I'll say, physical or simulated meaning. So if you see a value x on a wire or a variable, it means that the simulator cannot determine what the value of that signal is. It doesn't mean that in the real circuit it won't have a value. It could. It's just that the simulator cannot predict the value at that point in time. And there are different reasons why this could happen. If you've made conflicting assignments to a variable or a wire, you can end up with an x because in the circuitry that would be equivalent to connecting the same wire both to a logic 1 and a logic 0 at the same time. And that may have bad side effects on the circuitry, but at the very least, you'll get some intermediate voltage on the wire that doesn't correspond nicely to a 1 or a 0. Another way the value can be unknown is metastability. So if you have a flip-flop, you violate the setup or hold requirements, and you are simulating it, and of course this really only applies to simulation of the mapped version of the design. It doesn't have any meaning in the source code simulation. But when you're simulating a flip-flop, you violate those constraints. The output of the flip-flop can go temporarily to an unknown value or an intermediate value. So X does sometimes mean metastable, but it doesn't always mean metastable, although I find that students tend to refer to X as metastable no matter what's really going on. The key point is it just means that the simulator doesn't know what the value is. Not only does it not know whether it's a 1 or a 0, it doesn't even know whether it is stable or changing. This signal could be switching high and low at unpredictable times, and that would just end up being an X in the simulation. Okay, enough about that for the moment. The value Z corresponds to high impedance, and this really does describe a physical condition, whereas X may or may not. Metastability is a physical condition, but some of the other situations are just artifacts of simulation. In the case of Z, it represents high impedance, and you should by now have been exposed to something called a tri-state buffer, where you have an enable signal, and if the buffer is enabled, the output will force a 1 or a 0 on the wire. If it is disabled, the output is effectively disconnected from the wire, and it's referred to as a high impedance state. There is no, let's say, no resistive load present on the wire. There's no resistive path to, say, the supply voltage or to ground. And so the wire is in a high impedance state. And Z in the simulation represents this situation. We aren't going to use Z very much in 337, if at all, but if you happen to need to model, say, a bidirectional bus, where you would use tri-state buffers, or if you've learned about, say, open source, open collector, that type of logic output, those can also produce high impedance outputs. There are data types in Verilog, such as the bit type, that only support 1 and 0, but that means that the code using such a type can't represent these situations we just talked about. Now, the default type, if we declare a wire or a reg type, is going to have this 4-valued type of logic. Now, in the case of a wire, it's possible to have the wire driven by multiple sources, provided that only one of those sources has a non-high impedance value at a time. So if you have multiple drivers of a wire, anything other than Z will, I'll say, beats the Z. So if one of the drivers is Z, it just means the driver's not connected to it. So if you have another driver connected to the wire that's forcing a 1 or a 0, then that 1 or a 0 is going to be the value on the wire. However, if I have a value of X being driven onto the wire, which again is something that only makes sense in simulation, if I have something forcing an unknown value on the wire, then no matter what else is connected to it, there's no way of saying what the value on the wire is going to be. So it ends up being an X, no matter what. Now here I have a bullet, and I mentioned something for you to do. Draw schematics of situations that would give an output of X or Z, or really just look it up. Find your reference material for, say, a tri-state buffer in your 270 notes, or Google it, whatever you wish. those kind of circuits will produce or can produce an output of Z. For a situation that would give you an output of X, any circuit where you've got multiple drivers on the wire and those outputs have conflicting values, you're going to get an X. Okay. Final bullet here is to point out there is another data type that's not in Verilog, but it is in SystemVerilog, and that is the logic type. And really, you can use the logic type, or you can declare all of your signals as logic, and then never declare anything as wire or reg. And what will happen is the software will treat the logic type as if it was a wire or as a variable, depending on the situation. So if you assign a value using assign statements, it's going to treat it like a wire. If you assign a value from a procedural block, it's going to treat it like a variable. There is one way that logic is different from the reg type in particular, is that it cannot, or it will not, allow multiple drivers. So it will give you error messages if you have multiple drivers on it. In fact, that's a desirable thing. For that really by itself might be a compelling reason to use the logic type instead of the wire or reg. It just gives you better error detection. I am going to conclude part 1 of this lecture module with some comments on latches. It's already been discussed a little bit in the lab, but I wanted to point out that the common wisdom in industry among ASIC designers is that latches are undesirable. Well, that maybe would seem like an understatement considering what's written on this slide, and this is a quote from a book called the Synopsys Mentor Reuse Methodology Manual. And in the book it says, anyone using or designing with latches should be shot, we agree. Well, the red part's the quote from the book. The rest of this statement is a quote from an ASIC designer website, a very old website called deepchip.com. And if you look at the website, you'll see that it's very old. I think the appearance of it hasn't changed much since we started having web pages. Very old school, but very up to date in terms of the information about ASIC design, and it particularly focuses on the software that's used for doing ASIC design. And you'll find a lot of mentions of the software we use. Synopsys Design Compiler, Mentor Graphics, Model Sim, Orquesta Sim, Cadence Tools, which we'll use a little bit of later in the semester, and so on. Further down in the entry on deepchip.com, it has an additional comment, or actually somebody responded with an additional comment, and that was, anyone using or designing with latches will wish they had been shot. Well, I hope you don't go that far with it, but you may find yourself feeling like the latches are a scourge, and you'll be glad to be rid of them. There are special cases where latches may be necessary. We're really not going to have occasion in the context of 337 to use latches. And I should be careful to say, when we say latches here, we're talking about level sensitive latches as opposed to edge triggered flip-flops. You'll find in literature, in industry articles, in textbooks, like when you take 437, they will use the word latch in a more generic sense. But in 337, we specifically mean level sensitive devices. Here is an example of some code It's really overly verbose code. This function could be written much more compactly, but it illustrates some ways that latches can occur in the code, perhaps in unexpected ways. So I would like you to take a look at this code and think about how many inferred latches would be produced. And I suggest you pause the video, think about your answer, and then I will give you an answer and explain it. So pause now. Okay, coming back, let's look through it and see how many latches are we going to get from this. Well, I'll analyze the code. One thing I want to point out is setting a value of 0 in the declaration of this variable ends up having no influence on the circuit that's produced. So this does not save you from getting a latch, because one of the rules on latches, or one of the ways of describing how to avoid a latch, is make sure that every variable or every wire has a defined value for all conditions of the inputs to the circuit. So if I look down through the code, well, let's see, assign x equals x temp. Okay, well, I suppose x has a defined value at all times, assuming that x temp has a defined value, but it ends up just being a copy of that, so x doesn't create any additional circuitry. So I'm not really going to get a latch for x itself. But let's continue on. The rest of the module consists of this always COM block, and all of the functional code is in here. S underscore OR is assigned a value of logic 0. Okay, well, this statement alone guarantees that S OR has a defined value, because no matter what happens in the rest of the code, we have already assigned a value to S OR. Now, it's possible that further down that value will be overridden by some other value, but we're not going to get a latch on S OR. If this was the only statement in this block, S OR would be hardwired to a logic 0 or to ground. However, as I go down in the code, I see that when A or B is true, then S OR takes the value of 1. So really, S OR is just the OR of A and B, and it's not going to have a latch. But let's continue. If not A and B, then S NAND is equal to 1. Okay, great. So is S NAND defined for all possible situations? Well, if not A or B is true, it's defined as a 0. But what if this expression is false? What's the value of S NAND? Well, in general, it is not 0. When you're doing the source code simulation at time 0 in the simulation, it may have a value of 0, but once the simulation is in progress, if this expression is false, then S NAND will simply retain whatever the previous value was, which at the beginning of the simulation in source code would be a 0, but once a value of 1 has been assigned to it, there's nothing that's going to assign it back to 0. And in order for S NAND to hold that value even when this is false, it's going to need a latch to retain the value. So S NAND will have a latch. We've got one latch. Okay, we already talked about S OR. Now let's look at X temp. Well, if S NAND and S OR is true, X temp takes value 1. What if this expression is false? What's the value of X temp? In the case of X temp, there's no other value defined, so you will end up with a latch to retain the value of X temp when this is false. Basically, this expression will describe the enable for the latch that holds the value of x temp. And really in this design, initially x temp would be unknown, but once a value of 1 is assigned to it, it's going to hold that value of 1 forever. But it's going to require a latch to hold that value when this expression isn't true. So we've got a latch for x temp, we've got a latch for s NAND. Some people have thought maybe there would be a latch for x, but x is just another name for this output. When I assign a wire equal to some other variable or wire, it's still the same signal. Really, it still corresponds to the same piece of wire. It's just another name for it. So this does not cause an additional latch. So we've got 2 latches. Okay, that was a long explanation, but try to be very thorough. Last slide of part 1 is an example of some of the reasons we avoid latches, aside from taking seriously the advice of other ASIC designers who strongly recommend against using latches if you don't have to. And that is, suppose we have a counter, one of the simplest sequential blocks that we work with, and you've designed or implemented several counters when you did 270, and you would have implemented the counter using a register consisting of flip-flops, and it would have an edge-sensitive clock to it. And the input to that register would be a block that just increments the value of the count, which is the output of the register. Okay, so far so good. Looks like a counter, except that instead of a flip-flop based register, I've created a register, or I'm calling it the count latch here, that uses level sensitive latches. It's possible to create a counter this way, but it is risky. And I'm illustrating below what happens. So if the enable, because the value of the latch only stores the next count while the enable is asserted. Now it's level sensitive, which means the entire time this is asserted, the value of next count is being passed through the latch. That's why they're called sometimes transparent latches. The input just feeds straight through to the output. Well, think about what happens if this is enabled for too long. Suppose this was reset to 0 and it was initially not enabled, and that's like this waveform here, or really either of the set of waveforms below here, but let's concentrate on this one first. So if the enable is low to start with and we've asserted a reset, forced the value to 0, okay, great, no problem so far. We reset the latch, nothing bad happens. But now we enable the latch and we hold it for a while. Well, okay, the value of 0 propagates through the incrementer and gives us a 1. Well, if this path is faster than the time that the enable is asserted, that value of 1 will reach the latch, propagate through, come back around to the next count logic, increment, get a 2, and so on. So depending on the duration of the clock signal, this could end up giving you unpredictable results. For one thing, the speed of real circuitry is not completely consistent. The delays of the circuitry will vary with temperature, with variations during the manufacturing. It can be affected by noise in the environment. If the voltage on the power supply is a little bit low, circuit will be slower. Lots of things can affect the delays in this circuit. So if I hold the clock too long, not only will I get a race condition looping through the latch, but my value becomes unpredictable. And so when the clock or the enable is released, who knows what value we'll have at that point. Another way this may go wrong, well, it's part of the same way it goes wrong, but as these values are racing around here, not all the bits through the increment logic are going to propagate with the same amount of delay. So you might not necessarily even get a nice sequence of values like 1, 2, 3. Now the 0 will probably increment to 1, but as the count increases, the variation in the delay of the various bits will result in some garbage sequence. So in any case, you get unpredictable values, the clock is disabled, now we've got a value of who knows what. It'll vary from one copy of the circuit to another. And then we re-enable the clock, and for hereafter, the value of this thing is unpredictable. Now if we make the clock short enough, so now we'll go to the second set of waveforms, if we make the clock short enough, then this thing starts to act like a flip-flop. I think, well, great, why don't we do that? Because latches are smaller than flip-flops, so there's an advantage there. Well, it is a lot more difficult in real physical circuits, and particularly if they're operating at a very high speed, to make the clock pulse a small fraction of the overall clock period. So, in this example, I'm using the same clock frequency. It's just that I want the pulse to be much shorter. Well, like I say, it's hard to produce short pulses like this, and on a large chip with an extensive clock distribution network, the parasitics of the wires will cause the pulses to stretch and distort, and it becomes difficult to reliably feed a very short and necessarily fast rise and fall time signal throughout the circuit. So this isn't really a very reliable method of doing things. So that's not the only reason we avoid latches, but it's a fairly strong reason that we want to avoid unpredictable behavior, and we want to avoid having a design that's overly sensitive to the delays that are in the circuit. So, end of part 1.